What if your API call fails halfway through a workflow and you don't want to start from scratch? You'll see how LangGraph's durable execution lets you wrap API requests in a checkpointed workflow, so if anything interrupts the process, server timeouts, network issues, or even manual pauses, the system resumes exactly where it left off without repeating completed work. The example will show a simple graph with a single node making an HTTP request, but with persistence enabled so you can pause, inspect, and restart the workflow while maintaining state. We'll use an in-memory checkpointer for demonstration, though you could swap it for Redis or SQL in production.
From typing import not required. From typing extensions, import type dict. Import UID. From LangGraph, checkpoint, memory import in-memory saver. From LangGraph, graph import state graph start end. Import requests. Hash define a typed dict to represent the state. Class state type dict. URL, SDR. Result, not required SDR. Def call apostate, state. Example node, that makes an API request. Result equals requests, get state URL, text, 100 hash side effect. Return. Result. Hash create a state graph builder and add a node for the call API function. Builder equals state graph state. Builder, add node call API. Hash connect the start and end nodes to the call API node. Builder add edge start, call API. Builder, add edge call API end. Hash specify a checkpointer. Checkpointer equals in-memory saver. Hash compile the graph with the checkpointer. Graph equals builder. Compile checkpointer equals checkpointer. Hash define a config with a thread ID. Threaded equals UUID. UUID 4. Config, configurable. Threaded. Hash invoke the graph. Graph invoke URL. https://www.example.com config.
This demonstrates durable execution in workflow automation, a pattern that persists state between runs to enable pause, resume, and recovery capabilities. The core concept involves checkpointing workflow progress at each step, allowing the system to reconstruct its state after interruptions or failures. What makes this distinctive is its ability to handle non-deterministic operations and side effects safely by treating them as atomic tasks that can be replayed without duplication. The pattern works by separating state management from business logic, using a checkpointer to record execution history while the workflow graph defines the process flow. When interrupted, the system identifies the last successful checkpoint and replays from that point, using recorded task results to avoid repeating side effects. This creates a deterministic replay capability where the workflow behaves identically regardless of interruptions, with the checkpointer acting as the single source of truth for execution state. This approach solves critical problems in long-running workflows, particularly where human interaction or external system reliability is required. It prevents data loss from crashes, enables human-in-the-loop validation without restarting entire processes, and handles transient failures in external services. The trade-off is additional persistence overhead, but the durability guarantees make it essential for production workflows where consistency matters more than raw speed. Let's break it down.
From typing import not required. From typing extensions, import type dict.
Imports typed dict for type-safe dictionaries and not required for optional fields. This enables structured state management with explicit typing while allowing certain keys to be omitted.
Import requests.
Imports the requests library for making HTTP calls. This enables the call API function to fetch data from the provided URL, which is the core operation of this workflow.
Hash define a typed dict to represent the state. Class state type dict. URL, SDR. Result, not required SDR.
This defines the graph state schema using typed dict, enforcing type safety for node inputs and outputs. The URL field is required for the API call, while result is optional marked with not required since it's populated later by the call API node. This pattern ensures all nodes receive and return consistently typed data, preventing runtime errors in the workflow.
Def call API state. Example node, that makes an API request. Result equals requests, get state URL, text, 100 hash side effect.
This defines a graph node function that performs an API call. It extracts the URL from the state, makes a GET request, and returns the first 100 characters of the response as the result. The side effect comment indicates this modifies external state, which is typical for node operations in workflow graphs.
Return. Result.
This returns the API response as a state update. The dictionary structure matches the state typed dict, ensuring consistent data flow through the graph. This pattern maintains clean state transitions between nodes.
Hash create a state graph builder and add a node for the call API function. Builder equals state graph state. Builder, add node call API.
This code initializes a LangGraph state graph with a single node workflow where call API processes the input state containing a URL and returns an updated state with the API response snippet. The graph is configured as a linear pipeline start call API right arrow end with an in-memory checkpointing system to track execution state, then invoked with a sample URL and thread-specific config.
Hash connect the start and end nodes to the call API node. Builder add edge start, call API. Builder add edge call API end.
This defines the workflow's execution path. Start to call API initiates processing, while call API to end terminates the graph after completion. This linear flow ensures the API call executes exactly once per invocation.
Checkpointer equals in-memory saver. Graph equals builder. Compile checkpointer equals checkpointer.
This code sets up an in-memory checkpoint system, in-memory saver, to persist state between graph executions. When compiled with the checkpointer, the graph uses the threaded in the config to maintain separate state per thread across multiple invoke calls.
Hash define a config with a thread ID. Threaded equals UUID, UUID 4. Config, configurable, threaded.
This generates a unique thread identifier and configures it for state persistence. The threaded enables the in-memory saver, checkpointer, to track and resume this specific workflow execution, ensuring state isolation between different runs. This is the standard pattern for maintaining conversation or workflow history in LangGraph.
Hash invoke the graph. Graph invoke URL. https://www.example.com config.
This executes the compiled graph with the provided input and configuration. The invoke method triggers the workflow starting from the start node, processes through call API, and terminates at end, while the config ensures thread-specific state persistence via the checkpointer. This is the standard execution pattern for LangGraph workflows. LangGraph state management pattern. This example demonstrates the core pattern for building stateful workflows where each node transforms the state, with state graph orchestrating the flow and in-memory saver handling persistence between invocations. The threaded in the config is mandatory for checkpointing, and omitting it will silently disable state persistance.
The edge that connects nothing holds all paths.